In this question, we're given that a block of mass m is initially starting up a slope with speed u. The angle of the slope above horizontal is angle alpha. The coefficient of friction between the block and the slope is mu. Calculate the distance d the block strides up the slope before coming to the rest. So I think the first thing we could do is make a diagram. So suppose that's the block and we have the slope, and we're given this angle as alpha. The initial block, suppose that's the block, it travels at u, and we need to find the distance d that's covered when the block comes to rest. So at the bottom, at the start even, the kinetic energy will be at its max, and there won't be any gravitational potential energy. So the kinetic energy would be half m v squared, or in this case, half m u squared. This energy would be equal to the gravitational potential energy at the point where the block comes to a stop. So suppose it comes to a stop at the very corner, so suppose there, and say this height is x. So at this point, the gravitational potential energy would be mgh, and the h would be x, so mgx. Now we can equate these two equations because we know that energy has to be conserved. So half mu squared equals mgx. The m's cancel out, so we can get x on its own and say x equals u squared over 2g. That doesn't look like a 2. Now we also know that x over d equals sine theta, sine alpha. So we can get d on its own, x on its own, and say x equals d sine alpha. We can sub that into this equation and say d sine alpha equals u squared over 2g. Because we need to find d, we can rearrange for d and say d equals u squared over 2g sine alpha, and this is our final answer. Well, actually, we forgot to consider one thing. We're also given the coefficient of friction between the block and the slope to be given mu. So when the block is traveling up the slope, so suppose that's a block and that's the path where it's traveling, there would always be a force acting in the opposite direction. This will mean that some of the energy is lost by heating. So this won't be equal. There will be a loss of some amount of energy. Because we know that work done is the force times the distance, we can find out the energy lost by multiplying the force of friction times by the distance traveled. So if we draw a free body diagram for this particular mass, the force downwards due to the mass would be mg, and if we take components, this angle would be alpha. So the normal reaction force and would be somewhere there. This normal reaction force would be equal to this component of the weight. Now this component we can write as mg cos alpha, which is equal to the normal reaction force. Using force of friction, so FFR equals mu r, we can say the force of friction was mu times mg cos A, and the energy lost would be d times by mu mg cos A. This would be the energy lost by heating, so we can sub that back into the original energy equation we had. So we can say d times mu mg cos alpha. Now we can just do what we did before and sub in this x value into there. So if I just get rid of this, we would get u squared over 2 equals mg d sine alpha minus d mu mg cos alpha. We can take out d, so if I just bring it down, so we can say u squared over 2 Actually, in this case, we can also cancel out the m's, so we don't need to write down these m's. So u squared over 2 equals d brackets g sine alpha minus mu g cos alpha. We can get d on its own. So d equals u squared over 2g sine alpha minus mu cos alpha. So, and this is our final answer.